Very good day. I greet to Doctor. So my name is Chan Yao Xun and matrix number 223175. So today we will have an overview of first law of thermodynamics and second law of thermodynamics. So this presentation will cover introduction followed by first law of thermodynamics, second law of thermodynamics, conclusion, and last but not least references. Let us start with introduction to thermodynamics. What is thermodynamics? Basically, thermodynamics is a field of science that examines the energy and function of systems in their dynamic environments. In thermodynamics, there are four laws of thermodynamics. Only the first and second law of thermodynamics will be discussed later. Let's continue with first law of thermodynamics. What is first law of thermodynamics? The first law of thermodynamics is also known as the law of conservation of energy. It states that energy cannot be created nor destroyed. It can only be changed in a form from one form to another. In the first law of thermodynamics, the energy transfer that occurs in closed system and control volume will be discussed in the first law of thermodynamics. We have two forms of energy which are macroscopic energy and microscopic energy. Under macroscopic energy, it involves of kinetic energy and potential energy. Kinetic energy is due to the relative motion, while potential energy is due to the elevation in gravitational field. Under microscopic energy, it only involves internal energy, which due to molecular activity. The form of energy like kinetic energy, potential energy, and internal energy can be transferred across the boundary of a closed system in two different forms, which are heat and work. Heat is the type of energy that travels from one system to another under the driving force of temperature gradient. It means that heat will only be transferred when one system is hotter and the other system is cooler in terms of temperature. Only heat is involved in the energy interaction if it takes place because of temperature difference. Energy transfer in the form of heat will not happen when the boundary of the system is coated with insulated material. While work is the energy transfer to or from an object through the applied force along a displacement travel, work is also an energy interaction between a system and its surrounding, just like heat. As previously stated, energy can travel across the boundary of a closed system in the form of heat or work. Therefore, if the energy crossing the boundary of a closed system is not heat, then it must be work. Heat and work are vector quantities and thus consideration of magnitude and direction are important in doing calculation. A generally accepted sign convention for heat and work interaction is heat transfer to a system and work done by the system are positive, whereas heat transfer from a system and work done on a system are negative. Now let us move to the equation of first law of thermodynamics. In closed system, the equation is heat minus work done equals to change in internal energy plus change in kinetic energy plus change in potential energy. While for open system, just simply change the change in internal energy into change in enthalpy. To calculate the energy conversion efficiency, efficiency is the fraction of the desired outcome to the required input for a device. Application for closed system involve isobaric process, isochoric process, isothermal process, and adiabatic process. For isobaric process, the pressure is constant in a process. Work done by the system to against an external resistance as the heat supply. One of the example of system that apply isobaric process is the boiler system in power plants. During constant pressure, the boiler process occurs at fixed temperature, hence ensuring that heat transfer efficiently from the phase water to steam. If the pressure change, boiling point will be affected and will lead to inconsistent steam production. Under adiabatic process, the system is in an isolated condition and no heat is transferred during the process. One of the example of system that adiabatic process occur is refrigeration system. In a well-functioning refrigeration system, the condenser will release heat to the refrigerant that passes by while the evaporation will absorb heat from refrigerant that passes by the evaporator. So no heat exchange by the refrigeration system and hence it is adiabatic process. For isochoric process, in a constant volume process, the boundary will remain constant and no work is done by or on the system. The isochoric process usually happens in constant volume gas thermometer, nuclear reactors, and so on. For isothermal process, the pressure is inversely proportional to the volume under a constant temperature. The isothermal process was discovered to occur in industrial air compressor to prevent excessive temperature rise during compression in order to reduce energy loss in real life. Now let's move on to application for open system. Nozzle and diffuser. Nozzle is a device that increases the velocity of fluid at the expense of pressure, while diffuser is a device that increases the pressure of the fluid by slowing it down. Heat transfer in nozzle and diffuser is negligible. Nozzles and diffuser do not involve work and kinetic energy due to the high velocity. Now, let's move on to turbine and compressor. Turbine is a device that produces work, while compressor are devices that compressing the gas to very high pressure, which require work input. Heat transfer from the turbine is usually assumed to be zero because they are well insulated. The change in potential energy and kinetic energy is also assumed to be zero. Mixing chamber and heat energy. A mixing chamber is a device where two flowing fluid streams exchange heat via mixing. Heat exchanger is a device that let two flowing fluid streams exchange heat without mixing. Mixing chambers are usually well insulated and usually do not involve work. The kinetic energy and potential energy of the fluid stream are usually negligible too. Heat exchanger typically do not involve work interaction, and the kinetic energy and potential energy of the fluid stream are usually negligible too. Let us now move on to the second law of thermodynamics. What is second law of thermodynamics? Second law of thermodynamics was developed to determine whether the process is possible to happen by improving the adequacy of the first law of thermodynamics. It utilized to predict the degree of completion of chemical reaction and to provide theoretical limits for the operation of frequently used technical systems such as freezer, heat engines, and heat pump. There are two thesis statements which explain the second law of thermodynamics on the performance of the engineering device, especially the heat engine, which are Kelvin-Planck statement and Clausius statement. Then we'll eventually talk about the equivalence of the two statements. Limitation of the efficiency of heat engine from the basis for the Kelvin-Planck statement of the second law of thermodynamics, which states that it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a single thermal reservoir to the performance of an equivalent amount of work. A heat engine must reject some heat to low temperature reservoir to complete the thermodynamic cycle. To function properly, a heat engine must exchange heat with both a low temperature sink and a high temperature source. The Kelvin-Planck statement is one of the ways to express the second law of thermodynamics. It emphasizes the impossibility of achieving 100% efficiency in heat to work conversion in cyclic process. Clausius' statement is closely related to the working principle of the refrigerator or heat pump, which states that it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body. A refrigerator needs a compressor which is driven by an external power source to operate. It is known that heat will never be transferred from a cold medium to a hot medium. Clausius' statement does not mean that constructing a cyclic device that transfers heat from cold to warm medium is impossible. The net effect of the environment includes the use of energy in the form of work, as well as the transfer of heat from a colder body to a warmer one. Kelvin Planck and Clausius' statement are equivalent in their consequences, and the statement can be used as the expression of the second law of thermodynamics. Any device that violates Kelvin-Planck statement also violates Clausius' statement, and vice versa. Now let's move on to the Carnot cycle and reversible process. Carnot cycle consists of four reversible processes, which consist of two isothermal and two adiabatic, and they are executed in a closed or a steady flow system. The area of PV diagram under Carnot cycle means boundary work for quasi-equilibrium process. The area under curve 1, 2, 3 is the work done by the gas during the expansion of the cycle, and the area under curve 3, 4, 1 is the work done on the gas during the compression part of the cycle. The area enclosed by the path of the cycle, which is area 1, 2, 3, 4, 1, is the net work done during the cycle. Heat engine is a cyclic device and that the working fluid of a heat engine return to its initial position and state at the end of each thermodynamic cycle, and work is done by the working fluid during one part of the cycle and on the working fluid during another part. Difference between these two is the net work delivered by the heat engine. The efficiency of a heat engine cycle greatly depends on how the individual process that make up the cycle are executed. Under reversible isothermal expansion, TH is constant. The temperature of the hot reservoir is TH and the cylinder head is in contact with a source at temperature TH. The gas is allowed to gently grow and interact with its surrounding. As the gas expands, its temperature decreases. However, as soon as the temperature drops by an infinitesimal amount dT, some heat is transferred from the reservoir into gas, raising the temperature to TH. Thus, the gas temperature is kept constant at TH. Since the temperature difference between the gas and reservoir never exceeds a differential amount dT, this is a reversible heat transfer process. The amount of total heat transferred to the gas during this process is QH. In reversible adiabatic expansion, temperature drops from TH to TL. The reservoir that was in contact with the cylinder head is removed and replaced by an insulation so that the system becomes adiabatic. The gas continues to expand slowly, doing work on the surrounding until its temperature drops from TH to TL. The piston is assumed to be frictionless and the process be quasi-equilibrium, so the process is reversible and adiabatic. Now we move on to the compression part. Under reversible isothermal compression, TL is constant. The insulation at the cylinder head is removed, and the cylinder is brought into contact with a sink at temperature TL. The piston is now pushed inward by an external force. As the gas is compressed, its temperature tends to rise, but as soon as it rises by an infinitesimal amount dT, heat is transferred from the gas to the sink, causing the gas temperature to drop to TL. Thus, the gas temperature remains constant at TL. Since the temperature difference between the gas and the sink never exceeds a differential amount dT, this is a reversible heat transfer process. The amount of heat rejected from the gas during this process is QL. Under reversible adiabatic compression, the temperature rises from TL to TH. When the low temperature reservoir is removed, the insulation is placed back on the cylinder head, and the gas is compressed in a reversible manner, so the gas returns to its initial state. The temperature rises from TL to TH during this reversible adiabatic compression process, which complete the cycle. Now let's move on to thermal efficiency and coefficient of performance. Thermal efficiency is a fraction of the heat input that is converted to the net work output. It is also known as the measure of the performance of a heat engine. Thermal efficiency is a measure of how efficiently a heat engine converts the heat that is received to work. The efficiency of heat engine is measured by the ratio of the net work output to the heat. Coefficient of performance is used to describe the efficiency of a refrigerator. The objective of a refrigerator is to remove heat from a refrigerated space. To achieve this objective, it requires a work input. Now let's move on to the entropy part. Entropy is the amount of thermal energy in a system per unit temperature that cannot be used to perform beneficial work. Because work is obtained by ordered molecular motion, entropy is a measure of system molecule disorder or unpredictability. The concept of entropy provides valuable insight into the direction of spontaneous change in many common situations. Similar to energy, entropy is also property and has a fixed value at fixed state. The change in entropy between two specified states is the same no matter what path taken. Reversible or irreversible is followed during the process as shown in the figure beside. For an isolated system or simply an adiabatic closed system, the heat transfer is zero. And this equation can be expressed as the entropy of an isolated system during a process always increases, or in the limiting case of a reversible process remains constant based on principle of increase of entropy. Since entropy is an extensive property, thus the total property of a system is equal to the sum of the entropies of the part of the system. An isolated system may consist of any number of subsystems. A system and its surrounding likewise consists of an isolated system since both can be enclosed by a sufficiently large arbitrary boundary across which there is no heat, work, or mass transfer. Since no physical process is entirely reversible, it is assumed that some entropy is generated during the process, and so the entropy of the cosmos, which can be an isolated system, is always growing. The entropy generated by a process increases as it becomes more irreversible. If no entropy is generated during reversible operations, entropy generated equals to zero. The increasing entropy concept does not mean that a system entropy cannot decrease. A system entropy can decrease during a process. The opposite is true for entropy generation. The presence of irreversibility degrades the performance of engineering systems, and entropy generation is a measure of how much irreversibility exists during the process. The greater the degree of irreversibility, the higher the entropy creation. Thus, entropy generation can be used to quantify a process irreversibility. It is also used to create performance standards for technical device. Next, let us move on to isentropic process. Isentropic process is a process during which the entropy remains constant. The entropy of a fixed mass can be altered through heat transfer or irreversibility. As a result, during an internally reversible and adiabatic operation, the entropy of a fixed mass remains constant. Many engineering systems or devices such as pumps, turbines, nozzle, and diffuser operate adiabatically and work best when the process irreversibility, such as tribology, is minimized. The isentropic process enables us to define efficiency for the process to compare the actual performance of those engineering devices under ideal conditions. It should be recognized that reversible adiabatic processes are typically isentropic. However, an isotropic process is not always a reversible adiabatic process. The entropy of a substance increases during a process because of irreversibility may be offset by a decrease in entropy due to heat losses. So, in a conclusion, thermodynamics is concerned with the behavior of heat and temperature. Thermodynamics is also concerned with the direction of heat and other forms of energy. The first law of thermodynamics states that energy cannot be created nor destroyed, it only can be transferred. For the second law of thermodynamics, entropy will always elevate for any isolated system. The understanding of thermodynamics law can also allow the engineer to innovate a device with a higher efficiency with less waste of energy. So it is important for an engineer to know first and second law of thermodynamics, as this can help in various application problems. So here comes the end. That's all from me. Thank you.